We can't really talk about calculus until we spend a little bit of time talking about geometry. Now, if you look at the word geometry, there are two parts of geometry. Well, there's geo, which means earth, and metry, which means measure. So it's about measuring the earth. And so from the very beginning, math has really been about saying, hey, we need to figure out what's happening in the world around us. Now, why is geometry so important? Well, we're going to try to be describing things in space and trying to figure out, okay, what's happening to this? Where is it? Where is it changing? And so that's why we need to spend some time figuring out, okay, how do we go about describing where things are and where they're moving? So let's get into it. So let's start by talking about two dimensions, because, well, that's something we can probably handle fairly well. So there's two important things we want to talk about: position and distance. Now, how do we find position in two dimensions? Well, let's start with what's called the Cartesian coordinate system. Now, what is the Cartesian coordinate system? It's a system named after a philosopher, René Descartes. Now, legend has it that one day he was sick and laying in bed. And this was back before they had Xbox. And so he didn't have much entertainment, but he saw a fly up on the ceiling. And he thought to himself, maybe I can figure out where that fly is at any given time if I say it's this far away from that wall and this far away from that wall. In other words, by having a pair of distances, we can keep track of the location of where the fly was at. So that's sort of the basic underlying philosophy. When we talk about the Cartesian coordinate system, it says, let's assign location at any given point and associate it with a pairs of distances. And if we're in two dimensions, we'll talk about three dimensions in a little bit here. So what we'll have is a pair, x, y. Now what does x mean? Well, there's a central point, and we call this the origin. And then what we have are two directions. There's the direction which we call the x direction, and another called the y. And so when we talk about a pair, x comma y, it says, well, how much did you move in that x direction? How much did you move in that y direction? Now I know where I'm at. Good. So that's our location. Now, what about distance? Well, distance is based off of the Pythagorean theorem, which is really one of the best and most important theorems in calculus. And, so what does that say? Well, the Pythagorean theorem says if you have a triangle, and not just any kind of triangle, the right kind of triangle. So if you have a right triangle, then if you take the length of one side squared plus the length of the other side squared, it's the length of the hypotenuse squared. So if I have 2 points, so over here x1, y1, over there x2, y2, then what I can do is I can ask, how much do I move in the x direction? Well, the answer to how much I move is the difference in the x coordinates. So x2 minus x1. And then remember, we're talking about a measurement, so we have to make sure it's positive, which is why we throw in the absolute value signs. Same idea, y2 minus 1. That's a measurement of how much we move in the y direction. So take this side squared plus that side squared has to equal this side squared. Well, what is that side? The hypotenuse. That distance there, that's the actual distance between the 2 points. That's what we've decided we mean by distance. It's the straight line length between 2 points. So the distance squared, x2 minus x1 squared plus y2 minus y1 squared. You might say, well, what happened to the absolute value? Well, we squared it, and therefore the absolute value is no longer needed. Which leads us finally taking the square root. The distance is the square root, x2 minus x1 squared plus y2 minus y1 squared. So really, changing x squared plus changing y squared, take the square root, there's our distance, and we're good to go. All right, 2 dimensions, pretty good. Well, what do we do in 3 dimensions? Well, the answer is we have one more direction. But other than that, it still remains the same. So what we'll do now is we'll have three distances. We'll call them x, y, and z. Now, z, by the way, is a very fancy way to say z if you want to sound like you're European. Now, here we go. We again have our origin. So there's our origin. And then we have our three directions. And so we will follow what's called the right-hand coordinate system. And that's has it so that x comes out, y comes out, and z comes out. So as you go sort of counterclockwise, x, y, z. You can, of course, do a different coordinate system. In other words, put your axes in a different order, but it might change your orientation a little bit. And we'll get into orientation. Orientation is really quite an important topic, and we will see it showing up from time to time. So, what do we have? Well, what we have is, suppose I have a point. All right, and we'll say this is our point. X, y, z. Again, there's three distances. So x is how much we're going to move in the x direction. And then, of course, the y, how much we move in the y direction. And z, how much we move in the z direction. So, from this picture, there's a couple of important things we should be pointing out. So, there's things which we call the axes. Now, the axes, we've actually kind of marked them here. These are the x-axis, the y-axis, and the z-axis. Now, when you see x-axis, the idea is, well, only the x is the part that varies. So you'll notice that points on the x-axis have the form x, 0, 0. Y-axis, only the y varies, 0, y, 0. And for the z-axis, only the z varies, 0, 0, z. So the name kind of gives it away. Whatever you see on the name, x, y, z, well, that's what can vary, x, y, z. There's also things called planes. So you might, for example, have the yz plane, the xz plane, the xy plane. And you can think about these, if you think about things as walls and rooms. Well, when we talk about the xy plane, well, again, the name kind of gives it away. The xy plane, well, the x and the y can vary, and we set z to be 0. So what that corresponds to would be the floor down here. So that's our xy plane. Okay, so xy plane, notice that this is where z equals 0, and this is our floor. All right, well, what about the xz plane? Well, the xz plane, similar idea, except now it's the x and the z vary, y is 0. So where does that fit in? Well, if you think about, here's our y direction, so y equals 0 would say that we're over here. So this is our yz plane. It's our wall on that side. Okay, and then finally, we have the yz plane. The yz plane, well, that's where x is 0. X doesn't vary. So here's our x direction, so x equals 0 says that we are this other wall over here. Now, let's think about some various important points. So if I have x, y, z, well, the question might be, how do I get to there? Which is the right step to do first? Do I first move x, or do I first move y, or do I move z? And the answer is, you can really go in any order. First go in the x, then y, then z, or z, then x and y, any order you want. So I want to point out a couple of interesting points here. So suppose I start with x, y, z. What I can do is I can say, well, if I look at x, y, 0, that's the point down here. Now, what is x, y, 0? Well, x, y, 0, notice it's in the xy plane because the 0. All right, well, that's pretty easy. But is there anything else we can say? Well, this xy 0, this is the point in the xy plane, which is closest to our point xyz. All right, well, that's nice. Can we see why? Well, one of the nice ideas you'll see in geometry is this notion of when you're close as possible, you'll often see something about being perpendicular. So you can actually see in the picture that when we drop straight down, it's perpendicular. And so that's a nice way. Of course, the XY plane, very nice plane. Okay, well, same idea. If you came to this point, 0YZ, that's the closest point in the YZ plane. And over here, X0Z is the closest point in the XZ plane. All right, well, now what? Suppose I were to look, say, at this point, 0, Y, 0. What can I say is special about this point in relationship to the X, Y, Z? Okay. Well, in this case, what happens is if we look here, this is the point on the y-axis, which is closest to x, y, z. In other words, we have to say, look, if you're on the y-axis, your x and z have to be 0. Your y can be arbitrary. So if I want to be on the y-axis, okay, set x and z to be 0. Now, what's the right choice? Well, whatever the value for y is up in this corner, choose the same value for y. And then what will happen is that this line segment, it's actually going to be perpendicular to the y-axis. Again, the closest point. So whenever we talk about, okay, I have a point, what's the nearest point to the xy plane or the yz or xz plane? We can do that. But we can also talk about what's the nearest point to any axis. So that's sort of a nice system. Now, of course, these are really, really special cases. We might get to the point of saying, well, what if it's a different kind of plane? Because we can't talk about planes. There's lots of different types of planes, not just the floor or the walls. We might have planes which are sort of slightly slanted surfaces. And we'll get into that. It's a good topic. We don't yet have the tools yet, but we'll get those tools. We'll get the tools that we need. All right, so now we can talk about position. We know where we are. What's the next thing we need to talk about? Well, the other thing we need for geometry is distance. Now, in 2 dimensions, we have the Pythagorean theorem. What are we going to use in 3 dimensions? The answer is we're going to use the Pythagorean theorem plus plus. Well, really that just means we're going to take the Pythagorean theorem and just use it a couple of times, sort of bootstrap our way up, if you will. So, how do we do it? Suppose I want to know the distance between x1, y1, z1, x2, y2, z2. And when we talk about distance, we really mean saying, what's the length of the straight line segment that connects these pair of points? All right, so the goal is really saying, hey, what's this length here? Well, what can we do? One of the things we can do is say, let's break this down to an easier problem. What's an easier problem for us? Well, two dimensions. We can handle 2 dimensions. So we say, all right, so what can we do there? Well, let's turn and put a triangle in place. So we're going to put a triangle here, and where we take our box, we're going to go from one corner and go to the opposite side of the face, and it's still not just any triangle, it's the right kind of triangle. All right, so there's our right triangle. And now we say, all right, what about this new triangle that we've created? Well, this length C is also part of a triangle, where we go along the outer edges on the bottom. And again, it's a right triangle. So, what's our conclusion? Well, this length D, quantity squared, because that's the Pythagorean theorem, is this length C, quantity squared, plus the length squared of this opposite side. That's where the z2 minus z1 squared comes in. And then we say, aha, ha, ha, ha. Now, we look down here in this triangle, and what do we see? Well, it's exactly the same we were in 2 dimensions. So, change in x squared, change in y squared, that's c squared. And therefore, we get that the distance is the square root of change in x squared plus change in y squared plus change in z squared. Beautiful. Nice generalization. And it's clean. Now, of course, this does raise one small issue, which is we're going to have square roots involved. And square roots are an obstacle in some cases. And, practice. We'll see square roots coming up again and again throughout the semester. And whenever we see that at the heart, whenever there's a square root involved, ultimately it comes because there's a measurement of length in some way showing up. And so keep that in mind. When you see square roots, you should think, is there some measurement of length coming in? And can I use that information to figure out how to handle it? All right, one more topic before we finish up today. Now that we have distance, we can talk about something really nice, which are called spheres. So what's a sphere? Well, the definition is that a sphere is a set of all the points which are distance some number r, we call that the radius, from a central point, the center. And so that's HKL. Now, when I say the sphere, you should think of it like sort of the candy coating, if you will. So if you're familiar with M&Ms, they're not spheres, but they have that candy coating on the outside. And on the inside, that's the chocolate, and the outside, well, that's space, empty space. So, again, just the sphere just refers to just the exact outer surface. Now, how do we find the formula for a sphere? Well, the formula comes exactly from distance, because we're saying, look, there's a distance involved. So we want to say that the distance from the center, okay, so what's the distance? See, we go back to our distance formula. We can do that. We have the technology. So imagine that we have our distance formula here. So our distance is r. So let's put it here. Distance is r. R squared is change in x squared plus change in y squared plus change in z squared. That's exactly what's showing up here. See, this is the change in x squared plus change in y squared plus change in z squared equals r squared. So ultimately, the formula for a sphere, same for a circle, just comes down to saying, hey, there's a distance involved. And once we understand that, there's no mysticism about where the formula comes from. All right, so here's our picture. We have our center, HKL. We have our radius going out to the outer edge, and there's our set of points. Now, if we want to talk about the interior or the exterior, we need to change our relationship. See, currently, the equals is just the shell. If we want to be on the inside, well, what is that? Well, that says I need to be closer than that outer shell. So the interior would be when our distance is less than r. So the effect is we change the equality to a less than, so that the distance from my point to the HKL, the center, is smaller than r. That's the interior. If I want to be on the exterior, well, my distance should be greater than r. Okay, so there we go. That's how we can recognize things like interior versus exterior. Oftentimes, when you see things with equality, we tend to be describing the surface of something. When we start to see things with inequalities, now we're starting to describe sort of a solid of some sort, a shape in space. So that's the idea of spheres. Now, oftentimes we'll be handed a sphere, but we won't quite have it so clean. X minus h squared, y minus k squared, c minus l squared equals r. It won't be like that. Maybe it'll be written in some strange way. Like we'll have, x squared plus 6x plus, other stuff equals something. Okay. One of the things we want to be able to do is to manipulate. And by that, really it says, let's put things into more comfortable settings. The comfortable setting for a sphere for us is when we can write something into this format. So the x squared plus 6x is not in the right format because what do we have? Well, we really only want a single x. So what we really would like is we'd like to say, look, I want to replace this to be something that looks like, x something squared. So one of the important things is just as a callback to algebra. How do we do that? Well, I want to somehow figure out what do I need to put in here to get a square. In other words, how do I complete the square? So what's the way you do it? And quick refresher is the following. You say, look, if it were a square, so in other words, there's x plus a quantity squared, then what we would get is x squared plus 2ax plus a squared. That's what happens when you multiply out x plus a squared. So you say, okay, well look, I'm starting here, the x squared plus 6x. That's got to look like this piece. And now this something x squared, I want it to look like that part. So we say, all right, well, x squared, good, no problem. 2ax, well, see that 6 is going to match up with that 2a. So now we have the idea. Take whatever's in front of the x and divide by 2. In our case, 6 divided by 2 is 3. That's our a. Now we say, aha, if I plus the square of that number, so 3 squared would be 9, now this would be x plus 3 squared. Now you're like, woohoo, we did it. Except, got to be careful. We can't just add 9. That would change things. We don't want to change things. We want to make sure, look, we're still doing the same thing. We're just writing it in a different way. So how do we balance it out? Well, this is a beautiful old trick. If you've never seen it before, it's really cool. It's called subtract 9. Or really, what we can think about is if whatever you add, you also subtract, so that the net result is adding 0. So that's what you do. Now, one other slight word of warning. When we have x plus 3, where would be the x coordinate for the center? It would be -3, right? Because remember, it's a minus h. So if you think of it, this is really x minus -3. So that's one other thing to be mindful of. Because, these are small things. But of course, once we get the small things right, the big things, they tend to fall into place. So it's good to get practice and make sure we know what we're doing. Well, that's a good reminder. We should probably go and do some practice. All right, so thanks for coming, and see you at the practice soon.